Hello, everyone. It is a great pleasure to present to you today some of our research work at the Armed Forces Radiobiology Research Institute, which is a part of the Uniformed Services University Health Sciences USA. Being a researcher at the US government, let me first draw your attention to our disclaimer. The opinions, conclusions, and recommendations expressed or implied are my own and do not necessarily reflect the views of the Department of Defense or any department or agency of the federal government. This is Dr. William Blakely's lab members, and this is Dr. Blakely, who is the PI of the lab, and Dr. David Bolduc, who is the co-PI of the study. And first of all, I would like to thank both of them for the opportunity to present our work. The study is a great collaborative effort of many AFRRI and USUHS investigators who are listed here as co-contributors. This study was funded to Dr. Blakely by an intramural grant of AFRRI. And we have also recently submitted the results of this study to the Radiation Research Journal and is under review. The underlying goals of the study that I'm going to discuss in this talk are to characterize the natural history of a murine total abdominal irradiation model and to develop multiple parameter gastrointestinal acute radiation syndrome severity scoring system. We achieved our goals by using different methods that I'm going to brief you in the slide. We used MRI and CT scans to confirm organ and bone marrow locations. We used the linear accelerator irradiator at the Armed Forces Radiobiology Research Institute. And this is a picture of the system or the setup that we used. We induced different radiation doses to cause the severe injury. And mice were exposed to 0 gray, 11 gray, 13.5 gray, 15 gray, 15.75, and 16.5 gray. We then determined the changes in the body weights and compared them before and after irradiation. We also determined the clinical signs and symptoms associated with the gastrointestinal acute radiation syndrome, and then performed jejunum histopathology to examine crypt cell morphological changes and mucosal injury by using a 6th grade scoring system, which I'm going to discuss more in the upcoming slides. And all of these measurements were performed on day 1, 3, 7, and 10 after exposure. So to begin with, we wanted to first confirm the areas of irradiation and the organs involved in the total abdominal irradiation. We used MRI and CT scans to achieve these goals. So in this figure, the area of the field of radiation is represented in the shaded green rectangle overlaying the dorsal aspect of the mouse body. This is the MRI picture, which is a 3D MRI coronal anatomical view at different depths of a normal mouse. This gave us a relative idea of the location of the organs in the irradiation window. And this is the image or the CT image for identifying the areas of bone marrow. And the cartoon here is a representation of location of tissues and organs of interest, which helped us to collect tissues for various purposes. So after irradiating the animals at various radiation doses, we measured their body weights until the end of the study or endpoint. We then compared them to their initial weights before irradiation and calculated the weight changes. Then we graphed these into figures, and this figure shows the effects of total abdominal irradiation on mouse weight, changes which are related to the controls. We see that with increase in dose, there is a increase in decrease of the body weight. And the highest loss was seen in 16.5 gray. We see dose responses for animal weight changes as seen in figure B. And these changes are for day 1, 3, and 7 after irradiation, which were fitted to models. As dose increased, the weight decreased over time, as we can see from this figure. So both the figures A and B clearly show that the irradiation caused time and dose dependent decreases in relative weights, and higher doses uh, like 15, 15.75, and 16.5 grain resulted in greater decline of body weights. So one of our study goals was to characterize the natural history of the mouse total abdominal irradiation model and to develop a clinical sign and symptoms scoring system to assess the severity of gastrointestinal acute radiation syndrome condition. So a scoring sheet was designed to assess the animal's health based on the clinical signs and symptoms of 6 potential endpoints that I'm going to talk more in detail. So this is based on the IUCOG protocol at our animal facility. The 6 endpoints are appearance, respiratory rate, general behavior, provoked behavior, weight loss, feces, and diarrhea. So the case side measurements for clinical signs and symptoms were made twice daily. And the severity levels falls into different categories, as we can see here, as normal, mild, moderate, severe, and very severe. Each endpoint is scored individually, as is shown by the numerical scores, which are in pink. And depending on the total score, which is the tallying of the individual scores, one of the 3 outcomes of animal physical condition would be derived. Let me show you an example to make it easy. Okay. So as we can see here, the appearance has different scores, which are in pink, and the respiratory rate has different scores in brackets, which are in pink, and so on and so forth for the remaining endpoints. So for example, if the mouse is hunched or fluffed in appearance, we select 1, okay, and the total score will be 1. Suppose if the respiratory rate is 6, okay, we select 6. Similarly, if the general behavior is like decreased mobility, we select 2, okay, and the total will be obviously 2 plus 1 is 3. Okay, so and for example, for provoked behavior, if it says subdued even to stimulation, or it moves very slowly, then it's taken as 3, and so on and so forth. So if the body weight loss is, for example, 25 to 30%, greater than 25 to 30%, then we select 6. Okay, and now the total score is 12. And if the feces are soft or have diarrhea, so we select 2. Okay, and now the total score is 14. So how are these scores actually related to the actual severity of the clinical signs and symptoms? So if the score is if the total score, for example, is between 0 to 6 or less than 6, it's normal. However, if it is from 6 to 11, it's considered as morbid. And in this situation, we pay close attention to these animals, and we monitor them at least 3 times per day. And if needed, we notify appropriate personnel immediately. Suppose if the score is more than 12 or equal to 12, like we see here, the score is 14. So it's considered as moribund, and the animals are euthanized immediately in a human way because we don't want them to suffer. So in short, this is how we use the Murine morbidity severity scoring system to categorize the animals into normal or severely injured or very severe. So we then graph the clinical signs and symptoms with time after irradiation and with the dose for different radiation groups of mice. So as we can see from this figure, the irradiation caused dose-dependent and time-dependent changes after exposure. And the clinical signs or scores actually are prominent on day 7 and 8 after exposure. And the clinical scores kind of decreased after 8th day, but then they're still elevated compared to sham or control, as we can see here. Then we plotted to see the dose response. And as we can see from figure B, it's days 1, 3, 7, and 10 after radiation. Day 7 showed prominent or pronounced time dependence of dose, which in the elevated clinical scores. So both the figures A and B indicate that day 7 is kind of like a peak day of uh, severe clinical signs and symptoms. Okay, now the interesting part is here. How are all these connected to the gastrointestinal system, which is the main focus of our webinar? So since the GI tract is one of the most radiosensitive organ systems in the body, we wanted to study how these different radiation doses affect this system. And this is an excellent slide as it highlights various components of the GI tract. The GI tract, as we can see from this cartoon, it's a monolayer of crypt cells which provide stem cells for renewal of the intestinal epithelium. However, in case of radiation, these crypt cells are killed, which ultimately results in hemorrhage and ulceration. So our focus in this study was jejunum tissues. So we took this, we extracted the jejunum tissues and we counted the number of crypt cells per circumference and also assessed the crypt villi morphology. And these results were then used to quantify the degree of radiation-induced mucosal injury, which I'm going to talk in my next slides. So this is Dr. Julian Kiang, who is very patient to teach us the mucosal scoring and to count the crypt numbers. And she's one of our co-contributors of the study. Dr. Kiang has developed and used a modified way of assessing radiation-induced GI injury, and she has published a few papers based on that scoring system. And we have adapted the same scoring system from her. And I will discuss more details of those results in my next slides. So we have extracted the jejunum tissues from these control and irradiated mice, and we sectioned the jejunums, stained them with the hematoxylin and eosin, and then I scored these slices representing the injury from different doses at different time points. And images of these jejunum tissues represent a spectrum of morphological injury following radiation exposures, that is between 0 to 16.5 grade. So based on the modified mucosal injury scoring system developed by Dr. Kiang, as I mentioned earlier, the injury is scored on a scale of grades 0 to 5, which I'll show the representative images in the slide. So the black arrow represents the villi or the villus. And as seen in this image, grade 0 represents normal mucosa. Okay, and in grade 1, we see the developmental of subepithelial spaces near the tips of the villi and with a little bit of capillary congestion. In grade 2, there is an extension of the subepithelial space with moderate epithelial lifting of the lamina propria, which is here, and the tip of the villus breaks in this case, as seen in this figure. In case of grade 3 mucosal score, there is a significant epithelial lifting along the length of the villi and denuded tips, and the contents of the villus starts leaking. So in grade 4, while we don't have a representative image for this score, uh, the villus typically is denuded and exposed lamina propria and dilated capillaries and reduced crib depth, and also the number of cribs reduced drastically in grade 4. So finally, in grade 5, which is like two major scenarios, we have a situation where the mucosal growth grade is 5, where there is a disintegration of the lamina propria, there is and ultimately resulting in hemorrhage and ulceration. So we then graphed the mucosal injury scores with time after radiation and dose for the different radiation groups of mice. So the figure A, it shows a time course in days after the irradiation of the different doses on mucosal injury scores. So as we can see, the highest mucosal injury score was on day 7, similar to the previous results which we saw, which are very severe on day 7. So with injury scores dropping by day 10, which the reason I'm going to explain to you later in the next slide. Okay, and again in figure B, it's a dose response image in which we see the peak levels on day 7 again, as after irradiating with different radiation doses, especially for higher radiation doses as seen here. So based on the animal body weights, clinical signs and symptoms, and mucosal injury scores, we have seen that the maximum radiation effects were seen on day 7. So we have quantified these effects of radiation on crib numbers in jejunum for day 7 after exposure to different radiation doses. And this figure, as we can see clearly, it shows that with the higher irradiation doses, we have greater cell death. So based on the combined use of both clinical signs and symptoms, which I have previously mentioned, and mucosal injury scores, which I showed just now, a multiple parameter GI ARS severity scoring system was established for day 1, 3, 7, and 10 after radiation exposure. So this scoring system was designed to quantify the multiple parameter GI ARS severity for individual animals for the purpose of biomarker discovery. So the objective was to determine how mucosal injury correlated with visible clinical signs are induced from abdominal radiation, which would give us a time frame of when to look at for anomalies in candidate biomarkers. So it could potentially be of a very great value in predicting the gastrointestinal injury of radiation exposure. And based on the multiple parameter GI severity scoring system and the different endpoints like clinical signs and symptoms and histopathology, these can be categorized into different severity levels. The numerical scores again are marked in pink. and they are categorized into control, mild, moderate, and severe. So we then graphed this multiple parameter severity scores, again with time and after radiation and dose for the different radiation groups of mice. So this figure shows a time course in days after irradiation of the different doses, and it illustrates a progressive general increase of the GI injury. And this figure shows actually the mice survival at day 10 after irradiation with different doses, and clearly shows mortality occurring at 15.75 and above. So this is the reason why we saw a drop in on day 10, which I have shown in the previous figures, which is possibly because of the recovery and also because of the death of these animals. So to summarize the current study results, we have characterized the natural history of a murine abdominal irradiation model, and we used MRI and CT scans to categorize the organs and tissues we exposed. We then used the LINAC irradiations at the AFRRI facility for various radiation doses. And then we showed that the clinical signs and symptoms, including the body weights, have dose and time dependency, and we developed fitted models for radiation dose dependency for days 1, 3, and 7. And we also showed genome histopathology of these different groups of animals. We showed that the mucosal injury is dose and time dependent using the mucosal score injury score system, and we also developed a fitted model to report dose dependency, which was a decrease in Cribs per circumference at day 7. And combined use of these clinical signs and symptoms on genome histopathology, we were able to develop a multiple parameter gastrointestinal acute radiation syndrome severity scoring system. So based on these results, we hope or we aim to perform studies to correlate new biomarkers with the integrated severity using this multiple parameter GI-ARS severity scoring system. This is because it's very crucial to identify these biomarkers, because different mice models have different radiation responses or radiosensitivity. And the multiple parameter gastrointestinal acute radiation syndrome scoring system actually helps to characterize these biomarkers of effect independent of dose. So we are hoping that this study will be very helpful in the area of radiation research, and we look forward also for any further collaborations from any of the interested researchers. With that, I conclude my talk, and ready to take any questions. And this is my contact email address. If you're unable to ask and get any answers for your questions, please feel free to reach me out. Thank you.